All right, so this question, we're supposed to find the absolute maximum and absolute minimum values of this function, f of x equal to x squared minus 1 to the power 1/3 on the closed interval minus 3, 1 over 2 root 2. All right, well, because we're trying to find the absolute maximum and minimum values of a function f on a closed interval, you should probably be thinking that we should try to use the closed interval method. That's a very nice and efficient method for finding absolute maximum and minimum values of a function on a closed interval. So we should ask ourselves first, what do we need to apply the closed interval method? Well, all we need is a continuous function on a closed interval. So we just need to check to see that our function here is continuous on this interval. If it is, we can apply the closed interval method. Well, all of our functions are continuous on their domains, and the domain of this function here is the collection of all real numbers. Why is that? Well, if you take any number x, you certainly can square it, then subtract 1, and we can take the cubed root of any number at all. So this formula here will make sense for any real number x. That means the domain of this function is a collection of all real numbers. So this function is continuous then on its domain. It's continuous at all real numbers, and therefore in particular it is continuous on this closed interval, and that means that we can apply the closed interval method. So let's just write down to begin that our function is continuous on this closed interval. All right, so here's our solution. Okay, so note that f is continuous on its domain, which is, as we said, the set of all real numbers, and is therefore certainly continuous on this closed bounded interval minus 3, 1 over 2 root 2. All right, so therefore we can apply the closed interval method. To find the absolute max and absolute min of this function on this closed interval. All right, so what do we do first? Well, in the closed interval method, the first thing that we are supposed to do is we are supposed to evaluate our function f at the two endpoints. So we're going to evaluate this function f at the endpoints minus 3 and 1 over 2 root 2. All right, so 1, endpoints. All right, so first, what's f at minus 3? That's equal to, well, let x here be minus 3. We'll have minus 3 squared, which is 9. Minus 1 is 8, and we'll take the cubed root of that. So this is equal to 8 cubed root. And, well, we ask, what number cubed equals 8? 2 cubed is 8. So the cubed root of 8 is 2. All right, and now we need to evaluate our function f at the other endpoint, 1 over 2 root 2. So let's do that. Just we go. Okay, so we now need to evaluate f at the other endpoint. So f at 1 over 2 root 2 is equal to, and let me just rewrite what f is over here so that we can see it. F of x is equal to x squared minus 1 and the cubed root of that. All right, so we evaluate this with x equal to 1 over 2 root 2. Well, 1 over 2 root 2 squared, first of all, is 1 over 4 times 2, which is 1/8. So this is equal to 1/8 minus 1, cubed root of that. What's that equal to? Well, it's 1/8 minus 8/8, which is minus 7/8. Cubed root of that, well, that looks like minus 7. Cubed root of minus 7 then. Over the cubed root of 8, and because 2 cubed is 8, as we said above, cubed root of 8 is 2. Okay, so f at 1 over 2 root 2 is minus 7 to the 1/3 over 2. All right, so we'll just leave that for now. We'll think about how large or small that number is later. Okay, so now what do we do? Well, we evaluated our function f at the endpoints. The next thing that we're supposed to do in the closed interval method is evaluate f at all critical numbers in the interval, in this case minus 3, 1 over 2 root 2. All right, so we're now looking to evaluate f at the critical numbers in the interval. We could put closed interval or open interval here, it doesn't really matter. The worst thing that happens is that we have to evaluate f at the endpoints again. If I write down closed interval, I'll just write it the way we had it before, so open interval. So I'm looking to evaluate f at all critical numbers in this interval. All right, so what are these? These, well, the critical numbers, first of all, are all numbers x in the domain of our function, where either the derivative is 0 or it doesn't exist. In this case, we know that the interval we're looking at here, we know that this is contained in the domain of our function, so we can just write all x then in the interval minus 3, 1 over 2 root 2, where, so such that either the derivative is 0 or the derivative does not exist. Squeeze that in there. So, okay, so that's what we're looking for. So that means that we're going to have to now find f prime of x. So what we have to do now is find f prime of x to find out where it's 0 and where it doesn't exist in this interval. So what's f prime of x? Well, up here in yellow we have f of x, so we'll differentiate this using the chain rule, and we'll get that this is equal to differentiating the outer function. Leaving the inside, we'll have 1/3 x squared minus 1, reducing 1/3 by 1, we get minus 2/3, and now we have to differentiate what lies inside. The derivative of x squared minus 1, that's 2x. Okay, so we need to find then where this f prime of x is either 0 or where it doesn't exist. So let's just try to simplify it a bit. Well, we'll rewrite it as a fraction. This looks like 2x over 3 times x squared minus 1 to the 2/3. All right, so when is f prime of x equal to 0 then, and when does it not exist? Well, this is going to equal 0 exactly when? Well, this fraction gets to equal 0 exactly when the numerator is 0, which is to say exactly when 2x is 0, and that happens when x is 0. So this is true if and only if, I guess we could say, or when x is equal to 0. And let's note that this 0 is in the interval minus 3, 1 over 2 root 2. All right. And now we're looking for where it doesn't exist. So f prime of x does not exist. Exactly when? Well, when does this fraction not exist? Well, it's not going to exist exactly when the denominator is 0. Notice it doesn't matter what x you choose. You could square it, subtract 1, and then take its cubed root and square that. So this denominator does in fact make sense for all x. The fraction doesn't exist only when the denominator is 0. So f prime of x then doesn't exist exactly when this denominator is 0, which is going to happen when x squared minus 1 to the 2/3 is 0, which is going to happen when x squared minus 1 is 0, which is going to happen when x is either plus or minus 1. So if and only if x is equal to minus 1, or x is equal to 1. All right, now remember, we're looking just for those critical numbers in this interval here. Minus 1 is in the interval, but 1 is larger than 1 over 2 root 2, right? 1 over 2 root 2, it's actually less than 1/2, which is certainly less than 1. So 1 is not in this interval. So let's notice that that's the case. So this is not in the interval that we care about. Minus 3, 1 over 2 root 2. So in fact, the critical numbers that we were looking for, the critical numbers in this interval, those numbers x then, where the derivative was 0 or didn't exist, are exactly x equal to 0 and x equal to minus 1. Right, so x equal to 0 and x equal to minus 1. Those are the critical numbers in this interval, so let's write that down. So 0, x equal to 0, and x equal to minus 1 are the critical numbers that we were looking for. In this interval minus 3 and 1 over 2 root 2. So now what are we supposed to do in the closed interval method? Well, the first thing that we were supposed to do in the closed interval method was evaluate our function f at the two endpoints of our closed interval. And the next thing that we were supposed to do is evaluate our function f at the critical numbers in this interval. So let's do that. All right, so here we are. We need to then evaluate f at these numbers here. These are the two numbers. These are our two critical numbers in the interval that we care about. So here and here. All right, so now I'm just going to write down what f of x is again. Here it is. F of x, remember, is equal to x squared minus 1 to the power 1/3. So now we evaluate f at the two critical numbers, first at 0. What do we get? So let x be 0. I'll have 0 minus 1, which is minus 1. So minus 1, and then we take the cubed root of that. The question is then, what number cubed is equal to minus 1, and minus 1 cubed is minus 1. So minus 1 is a cubed root of minus 1. Okay, and now we need to, so there we evaluated f at 0, now we evaluate at minus 1. So here we are. f at minus 1 is equal to, right, so we're going to replace our x here by minus 1. We square it, we'll have 1. Minus 1 is 0. Cubed root of 0 is just 0. So we'll write that down. All right, so now what have we done? We've evaluated f at our critical numbers. All right, so let me find a good color here. Let's try red. All right. Okay, so we evaluated f at our critical numbers in the interval. We got 0, we got minus 1, and if we go up top, we can see the values that we got when we evaluated f at the endpoints of our interval. At minus 3, we got the value 2, and at 1 over 2 root 2, we got this number here. All right, so what are we supposed to do? Well, we're supposed to compare the values that f takes at the two endpoints, so this value and this value, and the values that f takes at the two critical numbers. We evaluated those below, and the largest of all these numbers is the absolute maximum value of f on our closed interval, and the smallest of all these numbers is the absolute minimum of f on this closed interval. All right, so we need to be able to compare the numbers 2 minus 7 to the 1/3 over 2, and minus 1 and 0. All right, so that is our question. Let me just write down what f of minus 3 was again. So let's write down, you don't have to do this of course, I'm just going to write down what our values were at the endpoints. At minus 3, remember, we had the value 2, and f at 1 over 2 root 2, there we had the value minus 7 to the 1/3 over 2. So there I have them all together, so you don't have to rewrite these, just so I can point. The question is, which is the largest and which is the smallest? Well, notice that this number is negative and this number is negative. This is 0 and this is positive. So 2 is definitely going to be the absolute maximum value of f. So let's write that down for step 3. Oops. Okay, so here we are. So in step 3, we compare all the numbers, and the largest of the numbers is the absolute max. And we just said that 2 is the absolute max. So let's write that down. F of minus 3, which is equal to 2, is the absolute max maximum value of f on our interval minus 3, 1 over 2 root 2. And the second thing we need to do is figure out which of these numbers is the smallest. All right, the smallest of these four numbers. Smallest of these four numbers is the absolute minimum value of f on this interval. So 0 and 2, those definitely aren't the minimum values because these two numbers are negative. The question is, which one is smaller? So is minus 1 smaller, or is minus 7 to the 1/3 over 2 smaller? And we need to be able to do this without a calculator. So how are we going to figure out which of these two numbers is smaller? Well, let's just note up here. So what I need, certainly I know how big minus 1 is, but I need to have some kind of an estimate as to how big this number here is. So let's just write up here, I guess. Let's note, minus 7 is less than minus 1, and it's bigger than minus 8. So if I raise these to the power 1/3, so the 1/3 function is increasing, it preserves order. The inequality is going to be maintained. And if I then divide by 2, again, because I'm dividing by a positive, the inequality is going to be preserved. So I did all that because this number that I see in the middle here now is the number that I was interested in. And I chose the numbers minus 1 and minus 8 because I know what their cubed roots are. And what do I see? Well, this is equal to cubed root of minus 1 is minus 1. I already calculated that, so we have minus 1/2 here. And what's the cubed root of minus 8? Well, what number cubed is minus 8? Minus 2 cubed is minus 8. So the cubed root of minus 8 is minus 2. So this is equal to minus 2 over minus 2, and I'm sorry about this. That's minus 1. So in fact, so this gives us a nice estimate for how large the cubed root of minus 7 over 2 is. It's smaller than minus 1/2, and it's bigger than minus 1. All right. In particular, minus 7 to the power 1/3 divided by 2 is bigger than minus 1. That's what I was interested in. This number is bigger than this number. Minus 1 then is the smallest of these two numbers, and therefore the smallest of all four numbers. Okay, so the value that f takes at 0 is the minimum value that f is going to take on this interval. So we can just write that down now. F at 0, which we said is equal to minus 1, is the absolute min of f. On this interval, minus 3, 1 over 2 root 2, and there we are, we're done. So let's just recall, what do we have to do? When you're using the closed interval method, it's really very easy. You just have to first justify that your use of the closed interval method is okay. For that, all you need to have is any continuous function on a closed interval. So you should say that your function is continuous on your closed interval. Then you evaluate f at the two endpoints. Next thing, you evaluate f at the critical numbers in your interval. Remember, don't evaluate f at all critical numbers, just those critical numbers in the interval. So one of the things that we did remember was when we found our critical numbers of f, we actually got 3 critical numbers of our function, 0, minus 1, and 1, but we didn't actually evaluate f at this critical number 1 because 1 wasn't in our interval. So it's important to only evaluate f at those critical numbers in the interval that we're concerned with. And then after we've done that, we have a certain collection of numbers. These are the values that f takes at the critical numbers in the interval and the values that f takes at the endpoints. We compare all of these numbers, not very many usually. The largest of all the numbers is the absolute maximum of your function on the closed interval, and the smallest of the numbers that you get is the absolute minimum of your function. In this case, our absolute max occurred at the left endpoint, minus 3, and the absolute min occurred at a critical number in the interval, at 0. Okay, that is all.